Now we're getting into the meat of what statics really is: equilibrium. Equilibrium is a state in which opposing forces and influences are balanced. This course is not about overall equilibrium, it's about static equilibrium. Static equilibrium is a form of equilibrium which occurs when an object is at rest. So all opposing forces are balanced and the object is not moving. In practical terms, this means that if we sum all the forces and moments, they must be equal to 0. Now, we approach equilibrium and we look at it kind of in two different ways. Well, we look at it three-dimensionally and two-dimensionally. So I'm going to start with 3D because 2D is a simplification of 3D. Now, any force in any direction can be broken down into rectangular components. We covered that when we covered vectors. So if we have a three-dimensional coordinate system, we can have forces acting in each direction. So we have a force in the x, a force in the y, and a force in the z. So in 3 dimensions, we know that the sum of forces in the x direction have to equal 0. The sum of forces in the y direction must equal 0. And the sum of the forces in the z direction must equal 0. Now, forces aren't the only thing we talked about. We also have moments to consider. When we have 3 dimensions, we have moments that act around each of the primary axes. So we have moments acting around the x, moments acting around the y, and moments acting around the z. We know that the sum of the moments about the x-axis, I'll use the @ sign, have to equal 0. The sum of the moments about the y-axis have to be 0. And the sum of the moments about the z-axis must be 0. So when we work in a three-dimensional coordinate system, we have 6 equations of equilibrium. And I'm going to call them E, O, for equations of equilibrium. So when you're working in 3 dimensions, you have 6 equations of equilibrium. You have no less, no more. These are all the tools you have to solve every problem. When we simplify this down into 2 dimensions, we lose the z-axis. So in 2 dimensions, we have forces in the x, and we have forces in the y. So we know that the sum of the forces in the x have to equal 0, and the sum of the forces in the y have to equal 0. Now, before we had moments acting around each of the axes, but a moment acting around the x-axis is acting in the yz plane. So it's not acting on the 2D plane we're looking at. So generally, we do not consider the moments around the x or the y-axis because they act out of the 2D plane we're looking at. The only one we need to consider is moment around the z-axis, because the moment around the z-axis, which would be acting in and out of your screen, is acting on this xy plane we've defined. Now, a lot of times when we're working in 2 dimensions, we don't even say sum of the moments around the z. We say the sum of the moments has to equal 0 because the only moments we're considering are the ones acting on the plane we're looking at. So in 2 dimensions, we have 3 equations of equilibrium to work with. No less, no more. Now, how does this work out? Here we have one blue particle. This particle has an x and y coordinate system coming from the center of the particle. It has 10 pounds acting down and to the left at an angle of 45 degrees, and it has 6 pounds acting at an angle of 30 degrees going up and to the right. I want to know what force will put this particle into equilibrium. Now when I say what force is a vector, so we need to come up with both a magnitude and a direction for this force. The first thing we want to do to work on any of this is break the 10-pound force and the 6-pound force into their x and y components. So, if we look at the 10-pound force, it has an angle of 45 degrees, which means at 45 degrees, both sine and cosine are the same, which means that when we say, if we want to find ax, or the x component for this, so let's say, we'll call this vector A and this vector B. AX is going to be equal to AY, and they're just going to equal 10 cosine of 45. And we find those components to be 7.07. When we look at BX and BY, they are going to be different because the angle there is 45 degrees. So BX is going to equal the cosine, going to equal 6 cosine of 30 degrees, which equals 5.19 pounds. BY is going to equal 6 sine of 30 degrees, which equals 3 pounds. So now we have two forces acting in the x direction and one force acting in the y direction. Or two forces acting in the y direction, sorry, because these are the same. So we can write two equations of equilibrium. We can say sum of forces in the x direction must equal 0. We can say sum of forces in the y direction equals 0. Since we're working in 2D, we have three equations ultimately. We have sum of forces in the x have to equal 0, sum of forces in the y have to equal 0, and sum of the moments have to equal 0. So we've talked about forces in the x, forces in the y, but we haven't talked about moment at all. And the reason we haven't talked about moment at all is because we're focusing on a particle, which is a point in space. So all the forces are acting around a singular point through that point. In order for us to have a moment, if you can remember, a moment equals a force times a distance, we have to have some distance. There is no distance for the nexus of all of these forces, so inherently, this equation of equilibrium is satisfied whenever you're looking at one point in space. So while we have a third equation of equilibrium, it doesn't help us here because we're looking at one singular space. If we sum the moments, we're going to find that they equal 0, so this is always satisfied when we're looking at one point. If we go on and write our equations of equilibrium in the x and y, we'll say the sum of forces in the x has to equal 0. So zero is going to equal, we have the vector A, which is acting down and to the left, which means its x component is negative according to our axis. It will be minus 7.07. We're going to have vector B, which is acting to the right, so it has a positive x direction, plus, so it'll be positive, so it'll be 5.19. And then we need to find out what this force, the x component of the force we're looking for is. So I'm just going to add F sub x in there. Now, this is saying F sub x is acting to the right. If this turns out to be true, the number we find in the end will be positive. If we find a negative number, all it means is this F sub x is acting to the left or in the negative direction. If we solve this, we find that negative 7.07 is bigger than 5.09, and if I move it to the left, it gives me a positive 1.88. So we find that f of x equals 1.88 pounds. So we have here the x component of the force we're looking for. If we sum the forces in the y, they have to equal 0, and 0 is going to equal the a vector is acting to the left and down, which means its y component is also negative, so that will be minus 7.07. B is acting to the right and up, so it will have a positive 3 pounds. And then I'm going to then add onto here some force component Fy, the same as before. If we solve this, it's going to tell us that Fy is equal to 4.07. And if we were looking for two forces, we could basically add these in here and say, if we add an additional force of 4.07 going up and add an additional force of 1.88 going to the right, we've put this particle into equilibrium. Now, I asked you not for two forces, but for one force. So what we're going to have to do is find the resultant and the angle for this force. So that gives us two unknowns. We want to find the resultant and the angle. So 1.88, 4.07. We have these two forces acting in the x and the y direction. We want to know the resultant, and the resultant we find from Pythagorean theorem. But we also want to know the angle. So we have two unknowns, so we're ultimately going to have to write two equations. Or not two equations, but we can find the resultant using trigonometry. We have two unknowns. So the resultant is just the square root of 1.88 squared plus 4.07 squared. This equals 4.48 pounds. Then I can use trigonometry and set up the triangular relationship. I have theta here. I know this is 4.07. I know this is 1.88. And I know this is 4.48. So I can use any of my trig identities to solve for my theta. I prefer to use tangent, so I can say theta equals the inverse tangent of 4.07 divided by 1.88. If you do this calculation, you find that theta is equal to 65.2 degrees. So 4.48 and 65.2 are our angle. So if I go in here and I draw in the resultant, it's basically saying that I have a force acting at an angle here of 62 degrees, and it has a magnitude of 4.48. And this one force acting up to the right will put this particle into static equilibrium.